Grenville's going to tell us about BiEntropy, TriEntropy and Primality, and I'm by one of very curious. It's a fantastic title, so looking forward to this. Take it away.
So this is my third presentation on BiEntropy related stuff for ANPA. First presentation was in 2013, where I'd invented BiEntropy and told about it. And then I did a paper a couple of years ago on the BiEntropy of knots. But I admit it's a considerable surprise to finding myself here again doing this. So I thought I need to introduce to people who haven't heard BiEntropy. So there's a little introduction there. Most of you will have heard of Shannon entropy, which is critically important. But even more important is these things called the binary derivatives, which are just extraordinarily powerful, and we'll see why shortly. So then I combined Shannon entropy, binary derivative, to create BiEntropy. Then finally we can show you how it's applied to the prime numbers, and then I generalize it to trinary arithmetic. So I'd just like to welcome my sister and brother-in-law here. My sister has just reminded me that she is the proud owner of her own personalised 200-digit prime number, which I gave her for her 40th birthday. So here we're talking about order and disorder. I've talked about order and disorder before as well in another context, but we live in a digital world, and here are some 8-digit binary numbers. And a binary number that repeats all ones or all zeros we might regard as being perfectly ordered. This third one, 0, 1, 0, 1, 0, 1, 1, 0, is mostly ordered, but it's not completely periodic because it's got this 1, 0 at the end instead of a 0, 1. So 0, 1, 0, 1, 0, 1, 0, 1 is regular. It's not disordered, but in fact it's periodic because there are repeating 0, 1s. And the period of the periodicity is 2, because it repeats every 2 characters. Here we have a repeating 1100, 1100, repeating with a period of 4, and so on. And then down at the bottom, we've got some unusual ones where there is no obvious pattern, and these are somewhat disordered. And so the task at the moment is to come up with a mechanism to place these strings in the relative order of their order and disorder, where perhaps the zeros and the ones are perfectly ordered there at either the top or the bottom of the list, and these disordered items at the opposite ends. And that's an interesting problem, because even in the 8-digit numbers, there are 256 factorial ways of putting these 8-digit numbers in an order. And John Anderson kindly pointed out that 256 factorial is 10 to the power of 508. So as we carry on, you might want to think about that number 10 to the power of 508 and the chances of making a chance discovery. Okay? So there's a lot of historical work done on randomness, order and disorder. I've been aware for some time of Pincus's work on approximate entropy, which is where I pinched the name BiEntropy. Marsiglia did his die-hard tests, which have been used very repeatedly over the years. And then we have an alternative approach to measuring order and disorder, which is the concept of algorithmic complexity. And this is where we, in order to establish the complexity of an item, we try and establish the length of the shortest piece of program code that will reproduce that string, and that's Colmore of complexity. And G.J. Chaitin, there's another GJC, Gregory Chaitin built up his algorithmic information theory based upon Kolmogorov's initial work. So it's an active research topic. And so this is Shannon's entropy. What we do is we count up the number of ones and zeros in the binary string, and it's and p is the proportion between 0 and 1 of the number of ones in the string. So Shannon's entropy, HP, is minus p log to the base 2 of p minus 1 minus p of log to the base 2 of 1 minus p. So basically you calculate a couple of proportions, take a couple of logs, add them together, and that's the Shannon entropy. And Shannon's entropy, of course, underpins modern comms theory and much else. And so this blue line here is the Shannon entropy as original, and so the maximum entropy of a sequence in Shannon's work is the one where there is the most variety, and this is where the number of ones and zeros is balanced equally. So a string that's got the same number of ones and zeros in it will have the maximum Shannon entropy. But I've discovered that it's very easy to enhance Shannon entropy by simply taking the nth power of the Shannon entropy, and we get a tighter curve, and so we can more easily measure the dispersion of the variety from its central mean of 0.5. So any questions? Just jump in.
On that deviation,
yep.
is there any meaning to, for example, the square, or is there any preferred power, in other words, of that width? Would you prefer a power there?
To be honest, I don't think it's been investigated.
Yes.
And so there is an essence of preference, as you'll see. I use Shannon entropy in the construction of BiEntropy for obvious and good reasons, but I think you'll see that there may be a way of altering it even beyond this to make it even more powerful. But the problem with Shannon entropy is that it mostly ignores any order and disorder in the string, so that this string here, which is periodic, 0, 1, 0, 1, 0, 1, 0, 1, and this string here, which is not periodic, which is 1, 0, 0, 1, 1, 1, 0, 0, both strings have got the same number of ones and zeros, i.e. 4 of each, and they've both got the same Shannon entropy, but one is periodic and one is not periodic. So there's a shortcoming in Shannon's work that ideally we should fix. Indeed, that is what we've done. But note that where the string is all zeros or all ones, Shannon entropy is 0. And so there's a very important piece of work by Mervyn Nasonson, 1971, which is almost uncited on the binary derivative. And so he formally defines periodicity, periodic sequences, and eventually periodic sequences, and gives us a load of very useful mathematics about how we use the binary derivative to detect periodicity. And so we detect periodicity by using the binary derivative. So this is the string x. The string s, here's the derivative, and the derivatives go from 1 to n minus 1. And so to compute the exclusive OR of a binary digit, a binary sequence, we simply take the difference between the adjacent bits. So this string here, 0, 1, 0, 1, 0, 1, 0, 1, to calculate this, starting from the right, 1 and 0 are different, so we write a 1. 0 and 1 are different, so we write a 1, and so on. So if the adjacent digits are different, we write a 1, and if the adjacent digits are the same, we write a 0. And so this periodic sequence goes immediately to all ones, and can anyone suggest what the next derivative of that sequence will be? All zeros. Yeah, and so this periodic sequence, by its second derivative, it's already gone to all zeros, and that's how we detect periodicity. And sometimes it takes the full set of n-1 derivatives to detect periodicity, or if there is no periodicity, then the last digit remains 1. And that is very, very powerful. So here are the properties of, or some of the properties of binary derivatives. So the derivative of a binary string is periodic with a period p, then the binary string itself is periodic with a period of p or 2p. If a binary derivative is all zeros, then the string has a period of 2 to the power of n for some n between 0 and n, and so on. So many properties of binary derivatives that we can use, and I think there are also some undiscovered properties of binary derivatives that have remained to be discovered. And of course, as far as I'm aware, there's been no work on trinary derivatives, where some joys may also lie. Another piece of very powerful work.
Are you going to tell us what a trinary derivative is?
No, because I haven't done it yet.
Okay, fine.
That's another day.
And how many beers does it take to get you started on it?
Neil, this work is an alcohol-free zone. Yeah. So Nathanson did the paper on binary derivatives, and that's very important. And Neville Davis et al. Did a paper on the statistical properties of binary derivatives. And this is the unbelievably powerful stuff that they've already done. So it remains for people like me. I don't have to do anything. I just have to cite their work. So if the ones and zeros in a string are equal, i.e. p equals 0.5, then the expected value of each bit of each derivative is also 0.5. with a calculable variance of exactly 0.25. And if the p is 0.5, none of the bits of every derivative are correlated. So obviously successive derivatives are algorithmically related, but the bits of each derivative are uncorrelated, and that's given as a formal proof. So in trying to design a function that would calculate the entropy of something, but do it properly, these are the points we need to take into consideration, particularly that we might need to evaluate all the derivatives. We might need to give different consideration to higher or lower derivatives. There are infinitely many ways we can weight the derivatives to give a particular derivative more, less, or the same importance. And of course, binary strings can be of arbitrary length. And so, BiEntropy is some function. There are many ways of doing BiEntropy. I keep inventing them every time I come to ANPA. So, some function f of the binary. Some function f of every binary derivative of the string. So it's a weighted average of the binary derivatives, and these are the basic choices of weight that we can use. And I'm going to be using the quadratic weighting method today. I had called it a polynomial weighting method, which indeed it is, but having worked through what it is I've done here, I've changed that to the word quadratic, which is correct, but also emphasises a particular point. So there it is in all its glory. That's the entropy. And so repeat after me. BiEntropy is a hierarchical quadratic weighted average of the Shannon entropies of a binary string and its first n minus 2 binary derivatives.
You've got hierarchical.
Sorry?
You've got hierarchical.
Hierarchical. Oh, they spelled it wrong.
Yeah.
No, thank you.
So if we translated that into German.
Yeah. So and so we can do BiEntropy on very short strings. And the strings 0, 1 and 1, 0 are the only perfectly disordered strings. Every other string, which are longer, are not quite perfectly disordered. The BiEntropy never reaches 1, but perfectly ordered strings of greater length do have can be perfectly ordered. And so here's a spreadsheet. I do everything in spreadsheets. So here's our binary string of length 4, and so here are the 2 derivatives. That's the number of 1s in each derivative, the length of each derivative, the p, the 1 minus p, the first logarithm, the second logarithm, the addition of the 2 logs, and the weighting. And so that string 1011 has a BiEntropy of 0.95. Which is, although that previous formula looked rather long and awkward, that's not the world's most complicated spreadsheet, I think. And so there we have it graphically. So here are the 2-bit binary strings 0 and 1, 0 and 1, with their respective BiEntropies. And so here's the BiEntropy of a 4-bit string. And you can see that down the diagonal, these are the strings with the lowest BiEntropy, and the 2 quadrants off diagonal have a higher BiEntropy. Okay.
If we go to longer strings, does that region with the highest BiEntropy reduce as a proportion of the total number?
Next slide. Next slide. And notice that we have finite states of BiEntropy.
Yep.
So the zeros, the 0.14s, the 0.41s, and the 0.95s. So there are finitely many states of BiEntropy, which is important. And so there's the BiEntropy of the 8-bit strings. So 0, 0, 0, 0, 0 is BiEntropy of 0. A periodic string 001, 001 also has a low BiEntropy, and so on. And you can see it's fractal.
It's fractal, yeah. Great. Beautiful.
Yeah, and notice the diagonal. Okay, so that diagram's been hanging around since 2013.
Is it published?
Yeah, it's on archive.
Good.
Yeah. It's been so that's been hanging around for a long time. Yours truly has stirred at it very often, but done nothing with it. So here's the applications so far. It's been cited 12 times. I have done a little bit of work on what's known as the prime constant. I've done knot theory, but I think you'd be interested to know that Sandia Labs, which is in the States, which is the equivalent of UK's GCHQ and Aldermaston combined, they've prominently cited BiEntropy in a recent patent to do with the generation of cryptographically secure random numbers. So Spooksville knows about this big time. So and of course, So the other citations it's got are in the field of cryptography and telecoms. So there's an algorithm, if you tap 2 mobile phones together, BiEntropy is being used to check the synchronization of the comms between the 2 mobile phones that then become cryptographically linked.
If you express this in a different number system, if you go to base 3,
yeah.
That BiEntropy is going to change, isn't it?
Yeah, and we'll show you how. It does generalise.
Good.
But it does totally have that.
Yeah, good. Yeah.
So here's an application in human vision. So here we have the Braille character set, the ISO character set, a low entropy character set, a high entropy character set, and a random character set, and they all have statistically discriminable BiEntropies. And so notice this one. This is the police checkerboard that appears where the police need to stop traffic, or in the UK. And BiEntropy of knots, because we can encode the various directions of motion of a knot into binary and compute the BiEntropy.
What is the BiEntropy of the trefoil?
There are numerous trefoils,
Aha.
so we can we can use BiEntropy to discriminate between alternating and non-alternating knots, just purely using the entropy of the form.
That's interesting.
Yeah, and so of course we can have knotted molecules, knotted DNA, knotted polymers, and so on, and they can, in principle, their entropies can all be computed using BiEntropy.
Does it differ if you change such things as hands on the?
It's out of symmetry that it won't.
Yes, the symmetry is that what you were saying?
So the symmetry in those diagrams you noticed, so
Yes.
it won't discriminate the symmetry. And so now we come to prime numbers. And so one day over Christmas, just gone, I sat down and coded up. It took about an hour. All the prime numbers in purple. Prime numbers below 256, and so 101, that's 5, it's prime. 000011 is 3, that's prime. And so you can see that most of the prime numbers sit in the disordered sector. Yeah? And there's only one prime that sits on the diagonal. And what type of prime do you think that one is? It's 0001. 0001. It's a Fermat prime. So the only primes that sit on the diagonal, i.e. any diagonal, are the Fermat primes, of which there are only about 5. And so we can then tabulate the prime numbers several ways. So we're just talking about the primes less than 256. So in the white area, which is 32 primes, 32 numbers, only one of them's prime. The yellow sector, 32 numbers, only one's prime. In the orange sector, slightly higher BiEntropy, there's 15 prime. And in the red sector, there are 37 prime. And the differences between those those two sets is significant at p less than 0.01, which is interesting. And then if we look more closely at the primes, not primes, the odds, the Mersenne primes and the twin primes, the differences become clearer, starker, and even more significant.
So if we took a prime which was in the white sector, it'd be rubbish at cryptography. One which had high BiEntropy and
and that's the basis of the Sandy Labs paint and why it's important.
Right.
And so BiEntropy essentially replaces Marseille's cluster of tests with one measure that's this measure scales quadratically.
Yes.
So for a number that's 1,000 bits long,
yes.
You're only doing 1,000 squared divided by 2.
So if that scales quadratically, is this exponential? Or have you looked at it?
No, this scales quadratically.
This is quadratic.
Yeah.
This is, okay. Right.
So, and this is the heart of the matter. What's known as prime density. So since 1896, it's been known through the theories of Hadamard and de la Vallée-Poussin that the prime density is scales as the natural logarithm of x, and so because x is low, I've slightly fiddled this because log doesn't quite fit the curve, but it does asymptote to log x for higher x, and so the sky blue line is log x, and the blue line is the number of primes. So the total number of primes less than 256 is 54. And here, to get this green line, which is the BiEntropy prime density, I've sorted the 256 natural numbers less than the 256 natural numbers into the BiEntropy order. and of course you can see that it's quadratic. And so I've invented a function that will automatically sort the natural numbers into ascending, quadratically, monotonically ascending prime density sequence. And of course the big game is whether or not the difference between the blue and the dark blue is Gaussian or not, and how big is it? And of course we can measure that quite easily. So these are the densities of the differences between natural and logarithmic prime density and bientropic and quadratic prime density. And as you can see, they're distributed identically. So, subject to a little bit of fiddling around, we should be able to prove that, well, we can certainly prove that that's easy to prove from the work of Davis and Nathanson, who are already cited. It's easy to prove that the bientropic prime density is quadratic, and I think it's only a small piece of work to show that because these relate to the same thing, that the difference between the natural and the logarithmic prime density is necessarily Gaussian also. And notice that the standard deviation is unity, which matches the theory. So plus or minus 3 about the mean. And that's. Any questions?
I'm very interested in these information measures and how they apply to machine learning. Particularly, when you look at periodicity, immediately I'm like, well, I know I can run a Fourier transform of a binary string, or I could go even a wavelet transform, and I could look at the complexity in this Fourier or wavelet space. The other thing which I see is, like, often we're taking a photo, so let's take a binary pixel photo of a circle. There's a 2D map, and I break that up into a string. Then I see scale. Like, I know I've got periodicity, but I've got something like a scale invariance in this. Do you have any views on how to turn this into distance metrics? Like, because there is a Shannon distance metric between two things, and how it might relate to Fourier transforms.
Well, in the binary space, I wouldn't mind betting that the Fourier transform and bientropy are analytically related.
But it gets you to triplets. It allows you to look at longer. I think you might be able to look at the longer.
Right. So if you go back to the human vision bit, we had the small characters in a 7x5 binary space. I think it does spot features and form. And that'd be a research project in its own right to go and scale that up and look at whether or not if you move the circle around, or you make it smaller or bigger, or you make it elliptic or not elliptic, what that does to the entropy.
There's a thing called Wesenstein's distance, or Earth mover's distance, which allows you to look at this scale invariance on this information.
Yeah, another project.
Yeah.
Yeah, if you go back to your Shannon formula.
Yeah.
I'm sorry, it's a long way back. No, the one before that, the Shannon. No, not the bientropy, but the Shannon.
Oh, right.
Entropy.
Yeah, that one.
And then you had the calculations for the different strings. I think it was the next slide.
Oh, next slide, that.
Yes, because you had the different strings and the value of the Shannon entropy. Because what you're actually here. So what you're actually measuring in the Shannon entropy is is not one particular string, but if you've got, say, 5 zeros and 5 ones, what are the number of different cases that you can make out of those 5 zeros and 5
And how many of them are periodic and how many are not periodic? Yeah, and that's the next piece of work, which is that I fortuitously chose Shannon entropy as the measure of central complexity or periodicity. And you're quite right that Shannon entropy correctly identifies all zeros and all ones.
Yeah.
But in the central part of that upturned U, we've got a whole bunch of strings that have an equal number of zeros and ones.
Yeah.
And Shannon entropy would say that they are of maximum disorder, but of course some of them are periodic and some of them are not periodic.
Yeah.
And of course periodic strings have an equal number of zeros and ones, so they naturally appear in the centre. So the next piece of work is to use the insight gained here to redo another version of BiEntropy that has a much better measure of periodicity. And the essence of this analysis is periodicity. And so I'm doing some of the theory of this next week, and the essence is that some numbers cannot be prime. Say the Fermat numbers, periodic numbers, can't be prime.
Yeah.
Did anyone know that? Did anyone taught that?
No. Say it again.
Save the Fermat numbers, periodic numbers cannot be prime in any base.
No. No. Anyone do that? No.
No.
Yeah.
A prime number is periodic in one base, so which is the base that's one less than itself. So 17, which is prime, is a periodic number in base 16 because it's 1.1. So every number is prime in at least one base, except the Fermat numbers, which are prime in two bases. Yeah. So the reason this works is because it fortuitously grasps some of the issues of periodicity.
Yeah.
But the next challenge is to generalise that so it formally grasps the true nature of all periodicity.
Yeah.
And we do another version of BiEntropy.
Yeah, because all this is capturing is that if you have 5 zeros and 5 ones, there are the most possibilities of creating different strings.
Yeah.
And if you have all zeros, there's only one possibility of creating a string.
That's right.
So that's all Shannon entropy is. So it's not looking at periodicity.
Could you?
No. So again, it was fortuitous that it works in this application.
Yeah.
Could you call the Shannon entropy then sort of a zeroth order entropy, where the first derivative is first order, second order, third order? Would that be a way of characterising the level of?
Do that offline. That's all right.
Okay.
Yeah. Well, my question is related to that actually, because one of the big criticisms of Shannon entropy is it can't deal with non-ergodic systems. It can't deal with living things where stuff emerges.
Right.
You've got to have a fixed alphabet. You've got to know what your alphabet is. So you've just got 0 and 1.
Yeah.
And then you calculate your entropy. So if you're going to different orders of entropy, presumably you can start to detect emergent categories, an emergent new alphabet.
Okay. Yeah.
Presumably you can do that, and then you can start to count. You can start to count that.
But I think there's another measure that might be interesting to look at, because you're absolutely right. I mean, there is only one string with all ones. You could weight this thing further by the number of possibilities in those things, which will reduce as you go down the derivatives. There's an absolute measure of
there's something
entropy at all levels.
Might as well share this with you, which is that I've just shown you the BiEntropy of the 8-bit strings. Of course, every string of any length greater than 256 differentiates into an 8-bit string, and so whatever result I've discovered here in this table generalises for all n, almost by it's either recursive proof or inductive proof, depending which way you do it. So I can just simply change this table so it reflects some of what's just been discussed to immediately improve the discriminatory ability in either this domain or other domains.
Yeah.
Well, that's good. Any more questions? Because we're way ahead of your time here. So we've just been small lunch.
Yeah, I'm not finished yet.
Oh, you're not good.
Okay, so that's where we were. Yeah, so the error in the prime number theorem, it's likely that it's Gaussian and of unit variance. So that will affect a lot of mathematics that's already been done. So I tested BiEntropy on the 32-bit numbers in a spreadsheet, because I'm a spreadsheet geek. And so what I did was I generated 10,000 random 32-bit numbers. I used a grunt method to divide by all lower primes. And I used the 10th power of the Shannon entropy to compute P10 BiEntropy. Sorted the data into natural and BiEntropic order, and generated the same density graph. So you can see here that here's the this is a Monte Carlo simulation of 10,000 random 32-bit numbers, and you can see that this is the logarithmic prime density and the quadratic BiEntropy prime density, and here's the curve fit. So this is log x, and if we square log x and divide by 2, we get the quadratic, which fairly closely fits the Monte Carlo. And so that's the distribution of the differences between the graphs on the previous on the previous page. So again, broadly normal, with fairly low standard deviation. I did try it on some 100-digit numbers, but the results, I could see the results, but they weren't sound enough to put them before you. So I had actually gone up to 100 digits in decimal 300-digit binary. So, because all primes are of the form 6k plus or minus 1, because 2 is prime and 3 is prime, it seems to make sense to see if I could generalise BiEntropy into TriEntropy. I had already noticed that BiEntropy does not detect periodicities of 3. And the way I discovered that, and you like this, a student in the Far East emailed me to ask if I thought BiEntropy would be any use in detecting the entropy of electrocution in fruit flies. So he was a neuroscientist, and he was proposing experiments that electrocuted fruit flies 12 times, and he wanted to look at the entropy of the resultant activity of the fruit flies. So I ended up writing a version of BiEntropy for him that was for 12 digits long, and when I was testing it, I noticed that it didn't detect periodicities of 3. So 0010101, which is periodic, its BiEntropy is 0.994, indicating disorder, but of course it's a periodic sequence. And so that gave me some motivation to go and develop TriEntropy. But to do that, I needed a trinary equivalent of the exclusive OR function, which proved a little tricky. But the way I eventually did it was using this truth table here, which is, John Amson informed me, it's called a pairwise trinary difference table. I won't attempt to explain it, but it's symmetric. It doesn't matter what order you put A, B and C, and most of the trientropies of the 3-digit sequence are dull, that it does actually work. So when we do the little spreadsheet to calculate TriEntropy, so 2, 4, 6, 8, 9 digit sequence, 3 to the power of 9 is about 19,000, are there? But notice here that there are fewer derivatives because we need 3 bits to compute, 3 tricks to compute one derivative. We consume the bits of the string, tricks of the string more rapidly. But here's the length of the string. So the length of the string, the number of zeros, the number of ones, the number of twos, the p, 1 minus p, and so on. Very similar. I did make a little mistake here actually when I did this. I did 2 to the power of k, not 3 to the power of k, but I managed to spot that error and fix it. But it does work. It does pick up the periodicities of 3. And then I did a trientropic prime density. So this graph has got 19,000 points on it. So you can see that we're getting the same or similar results, except that the difference between the trientropic and trientropic and natural prime density is in fact a cubic curve. You can see it's skewed slightly to the left. And again, I could have shown a different graph where I missed that out. We have a quadratic relationship between BiEntropy and Primality at least. That's using Shannon entropy. So at the moment we have coincidence of distributions of the errors between logarithmic integrand of x and pi of x and the BiEntropy of x and x squared. That was also observed in trinary, which is encouraging. And after a good 4 or 5 months of scratching my head, I think I'm reasonably sure I've got complete proof of how this all works for all x, certainly in binary, possibly also in trinary too. That's what I hope to do next week.
Thanks very much indeed. Questions?
I'd just like to see this slide again. How did you do trinary? I didn't get it. No, yeah.
Well, so a trinary string is composed of zeros, ones, and twos.
Right.
And so we need to. Here's the trinary derivative calculated using that table that was on the previous, which has 27 entries on it. It's 3 inputs, 1 output, 27 entries, and that gives us the rule for generating these trinary sequences. And wait for this. John Anson just emailed me a day or 2 ago to tell me that the TriEntropy rule is the same rule as the one that generates the Sierpinski gasket.
It generates the same rule as what?
That generates the Sierpinski gasket. So we're going down the rabbit hole now. Yeah, so we've got the table that tells us how to calculate each trinary derivative. We simply then count up the number of zeros, ones, and twos in a string. So we know the p of the string, and we just calculate it in the same way. Basically the same as BiEntropy.
More questions?
Have you thought about or examined how the entropy for the knots behaves when you change the knots, keeping the topological type the same?
Yes, I have. I've put it to the trefoil, and it's
and keep it a trefoil and move it around, change the...
Yeah, I've done exactly that. There are 72 forms of the trefoil in the cubic lattice space, and I can show that the entropy varies, and that the...
It certainly will vary, but then you have extremal forms of the knot, like you have at least lattice knot in your picture, right? In the trefoils, there are 72 forms, and they're all of the same length.
I've not examined redundant forms. I've only examined the entropy of the compact forms.
What's the variation? Do you remember?
Plus or minus 5%.
So they're all pretty close.
That's right. Yeah. Not papers online on archive.
Is there tri-redundancy?
Explain.
Well, I mean, the Shannon is kind of, the Shannon information, the H, is there in the context of constraint in one form or another, which is producing the entropy value that he gets.
Yeah.
So, and he's got, basically he takes the maximum entropy and divides it by, I can't remember what the equation is, but he's mathematically calculated redundancy. Can you do the same with this?
Probably. I'd have to look. Thanks, yeah. Thanks for the pointer.
The redundancy is really interesting.
Yeah, I've cited Shannon's paper, but I haven't actually read it yet. I've scanned it, but not read it in detail. But redundancy, I'll take a look at.
Yeah.
This Christmas.
We still have plenty of time for more.
Can we look at the previous slide actually? The one before. I mean, I just wanted to say that we just got out of the laws of form context. We were talking about difference and distinction, and that at the heart of forming this this derivative is sort of checking in the string whether one is distinct from the other in the nearest neighborhood.
Yeah.
And so this was kind of interesting to see the three-dimensional sort of three-valued extension of that.
Yeah, I think the point you make is that we're doing the difference based on adjacency.
Yes.
And of course, we could have M-adjacency, so that we could characterize strings by another related metric. More work.
If you did have such a system, so we changed, could you also filter the string by a multiple and n adjacency, reorder it, and then would that then show up, for example, through ordering adjacency that you see in the TriEntropy? Is what I mean?
Yeah, I see. Yeah, there may be information to be had about a string's properties.
So you take every first, every fourth,
every nth difference,
and then just reorder them at multiple levels.
Yeah,
that would also show up those kinds of in a simpler way, would it not?
Would it be simpler?
Maybe not.
Depends what we're trying to do. So I think the point now we know there's something interesting here,
yes.
And so I think the next step is to formalise it, yes. And then for everyone to be off and do their own thing.
Yeah.
There's basically too much to do.
Okay. Sorry, there's a guy called Robert Ulanovich who's a statistical ecologist, and he uses Shannon all the time to look at ecosystems. I mean, it's a long history of this, but he's particularly sharp on the utility. He believes the utility of Shannon for looking at particularly communication dynamics within ecological systems.
Yeah.
And he talks a lot about redundancy. He talks a lot about mutual information.
Yeah.
I mean, I'm thinking about this mutual information because the Shannon formula for mutual information suffers the same problem that you're identifying here. It doesn't address the periodicity.
Yeah, that's right. Yeah.
Or scaling variance.
No.
Or you can get some translation,
yes.
but you have heaps of issues with all of these things.
Yeah.
Yeah. So Ulanovich is really good. There's a paper called, if you just do a Google for Shannon exonerata,
right,
you'll find the paper. It's a brilliant paper.
Okay.
Shannon exonerata.
Right.
And what's the author?
It's Robert Ulanovich.
That'd be interesting. I can see where you're coming from. It's the dynamics of complex systems. Absolutely. Where you've got information sharing across, across, within, and you can more probably measure it.
Yeah.
In fact, I should probably mention there's an interesting paper on Dixra by Misra about the relationship between this prime problem and conventional physics. So there's the entropy BiEntropy I'm talking about, I've invented and played with, possibly has some relationship to theoretical physics.
Yeah.
I was just wondering if you pushed this into n-ary difference. I was most interested in quaternary difference, but and whether there's whether you only have to worry about the ends that are relatively prime to each other, but
I've certainly thought about n-ary, the n-ary problem.
Right.
I think there's probably going to be something interesting to do with, first of all, combining BiEntropy and TriEntropy and seeing what's in there. But I'm sensitive to the fact that the factorization problem is the reverse of this. And there's, maybe if we do compute some n-ary statistics, we can then estimate factorization properties in the Hamming space of the n-ary entropies. We might be able to get a steer as to what the properties of integers that have been used to compute that prime.
You can write an n-ary paper.
I call it n-ary had a little laugh.
So you have your next N conference presentations on that.
Sorry?
She was asking what is it? You asked about this joke. In-ary, like.
Oh, n-ary papers. Some paper.
Oh, I thought you
If you've got bits, was the next one trits?
Trits, yeah.
So is the next one quits?
Yep.
Oh, it's a comment.
And the 26th one is zits.
Russian alphabet would be SH as well.
Perhaps best leave it there and do some more jokes later.
Okay, well.
Thank you very much.